All right, we are going to go ahead and cover section 2.5 today over linear programming. So linear programming, this is a method that uses our linear equations and our linear inequalities to determine the optimal solution of a certain situation. So we're going to talk about a few examples here, but then we're going to put it in the context of some real world applications and some different problems here so that you can see how that connects to the real world. So for finding the optimal solution, we are going to start with using Desmos to graph the system of inequalities. We're going to use Desmos because we can click on the different points that we need and it'll list them for us instead of using our graphing calculator. And we're going to be using inequalities, so we need to see the different shaded regions of our graph. Okay, so a little different than our graphing calculators. So when we use Desmos to graph the inequalities, these are called the constraints. Okay, so we're kind of creating these constraints of with our different functions for that certain situation. We're going to find all the vertices, so those different intersections of all of our system of inequalities, and this is going to define the feasible region. So we have our constraints, that's going to limit our graph to a specific area. That is the feasible region for that certain problem. And then third here says, identify the vertex that maximizes or minimizes the objective function. So we're going to use those different vertices or intersections that we find once we graph, and it's going to create our maximum and minimum. And then depending on the context of the situation, we'll be able to determine kind of the best course of action, whether we want to look at that maximum or look at that minimum. Okay, so I'm going to go ahead and take my different constraints here, or my inequalities, and go to Desmos, and I'm going to graph them. Okay, so I have these graphed here. On Desmos, just click on a different box for each one so you can see these. We want to look at each of our vertices. So I'm going to look at each intersection on my graph for where each of these inequalities cross. Okay, so I have my three vertices, 2, -1, 2, 2, and 8, -1. Okay, so I'm going to go back to my notes. I'm going to put these vertices in the table for question 1. All right, so I said we had 2, -1. We had 2, 2. And we had 8, -1. Okay, so I'm listing my different vertices. This is telling us the objective function. We need to find the minimum based on this. C is equal to 3x plus 4y. So it's telling us the minimum value is going to be represented by 3x plus 4y. We just have to figure out which vertice is going to give us that minimum value. So I'm just going to take my x and y values. So I'm going to have C is equal to 3 times my x value plus 4 times my y value. And I'm going to do this for each one. 3 times my x value plus 4 times my y value. Okay. So I'm filling those in. Use your calculator to find these values. So I got 2, I got 14, and I have 20. Okay. We want the minimum value. Well, 2 is my lowest number here. So when I answer this question below, 2 is the minimum value for C, and that occurs at 0.2, -1. Okay. And there was a typo on my notes here. So it said maximum, but it had us look for the minimum. So I changed that to minimum. So we're looking for, of the values that we get over here in that C column, looking at whether it's asking for minimum or maximum, and figuring out what value meets that requirement. Okay. Okay. Let's look at our next one here, number 2. So we have x is greater than or equal to 0, y is greater than or equal to 0. Then we have a couple other inequalities. Y is greater than or equal to 2x minus 4, and y is less than or equal to negative x or negative 1x plus 5. So we're going to do the same thing. I'm going to go ahead and go to my Desmos. I have these typed in here so I can see my system of inequalities. And I'm going to click on each vertex so I can see where they are. I kind of think of it as they're forming this like shape in the middle, okay, where they're all crossing each other. So if you have 4 lines, you're going to have 4 vertices because it's going to cross each one four times, okay? So I have my ordered pairs 0, 5, 0, 0, 3, 2, and 2, 0. So I'm going to go back to my notes. I'm going to go ahead and fill in my ordered pairs here. And this time it is telling us to look for a maximum, and we find that maximum at p is equal to x plus 3y. So I'm taking my x value of 0 plus 3 times my y value of 5, or 0 plus 3 times 0, 3 plus 3 times 2, so substituting in those x and y values. Okay. All right, so when I go ahead and find this, I got 15, I have 0, I have 9, and I have 2. All right, so this time it's asking us for the maximum value. So make sure that we're paying attention. It's asking for the maximum. My highest number I see is 15. So I know that 15 is the maximum, and this occurs at 0.05. Okay. Okay, let's keep going. We have some more constraints with our linear inequalities here. X is greater than or equal to 3, y is greater than or equal to 4, and y is less than or equal to negative 2x plus 14. We're going to graph, find our vertices, and then search for our minimum on this one. All right, so I have these typed in. I am looking at my graph. I kind of see that it is forming a little triangle here in the middle. So I'm going to click on each vertex. I had 3 inequalities, so I should have 3 vertices. I have the 0.38, the 0.34, and the 0.54. So 3, 8, 3, 4, and 5, 4. So I'm going to go ahead, substitute these in. All right, 5 times 3, 15 plus 8, we should get 20, wait, hang on. 5 times 3, 15, plus 8, 23. 5 times 3, 15, plus 4, we get 19. 5 times 5, 24, 25, plus 4, 29. All right, we're looking for the minimum at this point. So my lowest value here is the 19. So that means that my minimum value, 19, at the 0.34. All right, one more example, and then we'll get to our real world examples so we can see what this looks like in those types. All right, and then on number 4, it was the same graph as number 2, but it's asking us to find a different objective function, so we'll be plugging in to a different expression. So it's my same ordered pairs, 0, 5, 0, 0, 3, 2, 2, 0. I'm going to go ahead and go back to my notes here. I'm going to fill in, I had 0, 0, I had 0, 5, I had 3, 2, and I had 2, 0. All right, so 2 times 0 plus 6 times 0, we get 0. 2 times 0 plus 6 times 5, we should get 30. 2 times 3 plus 6 times 2, we got 6 times 2 is 12. 2 times 3 is 6, so we should get 18. And then last one, 2 times 2 is 4. 6 times 0 is 0, so we should have 4. All right, and maximum value on this one. 30 is my biggest number, so that is my maximum value. That occurs at 0.05. Okay, so now just to think about when we're actually trying to find that minimum or maximum value, what that actually means in a real scenario, okay? So on 5 and 6 here, we are going to set up the constraints and the objective function for these scenarios. We're not going to solve them, but we just got to have ways to come up with our different constraints from here, okay? All right, so it says the area of a parking lot is 1,200 square meters. A car requires 6 square meters and a bus requires 30 square meters. The attendant can only handle 60 vehicles. If a car is charged $2.50 and a bus is charged $7.50, how many of each should be accepted to maximize income? So a lot of these examples are going to be maximizing profit, maximizing income, because that's our goal. So when we're trying to find that maximum, we're trying to figure out what ordered pair or what amount of each will make the most sense in our context to get us that maximum profit, okay? Okay, so I'm gonna kind of start with defining my variables. So I'm just gonna go ahead and do X and Y. Let's say X is cars and Y is buses. Because if we look at this last question, how many of each should be accepted? So we need to figure out how many cars and how many buses will maximize that income. So defining our variables is very important. The first thing I want to start with is we cannot have a negative number of cars or a negative number of buses. So I'm going to go ahead and get rid of any of those negatives by stating one of my constraints. X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. We can't have a negative number of cars or buses, so we're going to set those up so that our solution makes sense in this context. The next thing I'm going to look at is the attendant can only handle 60 vehicles. So if I take my total of cars and buses, it cannot be any more than 60. So the next one I'm going to write is X plus Y has to be less than or equal to 60. So we can be right at 60, that's that or equal to, but we have to be less than or equal to because the parking lot will not hold more than 60 cars, okay? All right, last we're going to deal with the square meters part of things. So 1,200 square meters is my total. And then we know that a car takes 6 square meters and a bus takes 30 square meters, okay? So if I have a car that takes 6 square meters, I'm going to do 6 times the number of cars plus 30 times the number of buses, so 30 times Y. And all of that square meters needs to be less than or equal to 1,200 because there will not be any space if we go over. So we have to keep it less than or equal to, okay? All right, so those are all of the constraints with the information we're given. The next part we need to look at is setting up our objective function, okay? We are trying to come up with the profit or the maximum income, the maximum money we can make from this parking lot attendant. So I'm going to go on to this last part. If a car is charged $2.50 and a bus is charged $7.50, how can we use that to find our maximum profit? So I'm going to say P is equal to $2.50. That is how much a car is charged. So I'm going to put the X by that. And I'm adding that to $7.50. That's how much a bus is charged. So I'm putting a Y by that. So in order to find that profit, we would look at all of those vertices we came up with once we graphed our constraints. And then once we plug those in, we would be able to see which vertex got us our maximum income. Okay. let's look at another example here. This one, lots going on, okay? I'm going to start with this last part. What ratio of belts and wallets will produce the most profit within the constraints? So we have a leather company. They make belts. They make wallets. They talk about how much time it takes to cut and sew these and how many hours a week the machines are available. So we are going to define our variables. I'm going to say that X represents the number of belts they can make. And then I'm going to say that Y represents the number of wallets they can make. Okay? Okay, so again, I'm going to start with that X has to be greater than or equal to 0 and that Y has to be greater than or equal to 0. These are going to be very common constraints that you use because we can't have a negative number of belts. We cannot have a negative number of wallets. They have to make some number of them, okay? It could be 0, but it can't be any less than 0. So the next thing I want to look at is it talks about how the belts require 2 hours of cutting time and the wallets require 2 hours of cutting time. And the cutting machine is available 12 hours a week, okay? So this one's a little trickier because the different information is all broken up throughout the problem. So I'm going to take belts require 2 hours of cutting time. Well, I'm going to have 2 hours times the number of belts plus wallets require 3 hours, so I'm going to do 3 times the number of wallets, okay? The cutting machine is available 12 hours a week. We cannot go over the amount of hours that it's available, so I have to keep it less than or equal to the 12. Okay. So making sure we're kind of thinking of how these sentences in our actual problem are broken up. We have, this information was all about the cutting time and the cutting machine. Next, I'm going to look at the belts require 6 hours of sewing time. Wallets require 3 hours of sewing time. And the sewing machine is available 24 hours per week. Okay, so I'm going to set up a similar inequality here. 6 hours of sewing time for the belts plus 3 hours of sewing time for the wallets. And it has to be less than or equal to my 24 hours that the machine is available. So I have all of my constraints. The last piece we need to look at is how much money will be made for each belt and each wallet, because we want to look at producing the most profit, okay? So producing the most profit is our goal. So I'm going to start with profit, or P, is equal to, and now we're back up here to the top. Each belt nets $18 in profit, and each wallet nets $12 in profit. So I'm going to put the 18 by the belts for X plus the 12 times the Y for wallets. We would look at our constraints on a graph, look at the vertices that come up, check each vertice into plugging them into our objective function, and then which one produces the highest number would be our maximum, and then that vertice or that vertex would get us our maximum profit. So we can see how this fits into some real world problems, making sure that we can find how to reach the maximum profit.